The Poisson distribution is a discrete distribution named after a French mathematician, of course, named Poisson. All right. And in fact, there is a link between the binomial distribution and the Poisson distribution. Let's take an example to illustrate that link and give you some more insight about it. If you consider the case of a binomial distribution, for example, you might say that x follows a binomial distribution with a certain parameter n and a certain parameter p. Now, when you are working with x was representing a certain number of successes out of a fixed out of a fixed number of trials. That's how x was being represented as a certain number of successes out of a fixed number of trials. Now, an example would be the case of x representing the number of heads obtained if you were to toss 3 coins. If n is equal to 3, you were looking for x is equal to 2 earlier, or you were looking for x equal to 1, things like that. So that's a little bit how the binomial was and what you were looking for from a binomial. You were looking for the number of trials, number of successes, sorry, out of a fixed number of trials. That's, by the way, a way of determining whether a question is to be based on a binomial distribution or something else. You can verify that just by looking at the number of successes out of a fixed number of trials. What about, so the case of a coin here, we took the example of a case of a coin, 3 coins. What about a Poisson distribution? The first thing is that you would normally say that x follows a Poisson distribution. X follows a Poisson distribution. The first thing is that the parameter is going to be a little bit different from this one, but it's going to be defined as lambda. It depends on notation. Sometimes some books write it as mu and so on, but we will use the notation lambda in this course. Now, when you say that a certain random variable x follows a Poisson distribution, what we need to understand is what does this x represent? Here, there is a difference between what we had before and what we had now. Here you are still referring to a certain, if you want, number of successes or certain occurrence of an event within a certain time interval or space. And these events are meant to be random. But when you have heard what I said here, I did not refer to any fixed number of trials, because the number of trials here is basically undefined. It could be an infinite number of trials that can be considered as well. So what is happening here? Let's take one example. I'll take the example of a number of accidents. Number of accidents at the roundabout of let's suppose réduit, at the roundabout of réduit over a certain day or a certain week or day, whatever, certain time interval. What is going to happen here when you are referring to the number of accidents? You will have to understand that you are not referring to the number of accidents out of a fixed number of accidents that you have. You see, you cannot say that I'm going to evaluate the probability of having 2 accidents during a day out of, let's suppose, 10 accidents. That does not make any sense here. So you see already one of the difference that you have is that the number of trials is not defined, though the number of successes is kind of similar here. You still have a kind of success which is defined as the number of an accident, but the thing is that there is no fixed number of trials. So in other words, n can be considered to be an infinite number of trials if you want. Okay. So that's already one of the difference that you have between the binomial and the Poisson distribution. What's the next one? Just like in the case of a binomial, you had p, which was constant. Here, we won't be referring to p as being constant, but we will refer to np being fixed or constant. That's the other thing that we have to note. Here we were working with p, but here we are going to refer to np being constant. And in fact, what is np? np is the expected value of your random variable x in the binomial distribution. All right, it's your expected value of x in the random variable. And in our Poisson distribution, you will see later on that the expected value of x is lambda. So if you are talking about a limiting case of a binomial distribution where lambda is equal to np, which is going to be constant from trial to trial, and like here, if you are referring to a binomial where the expected value of x is np, and it is a constant from trial to trial, and the uh, number of trials is undefined, it's going to be infinite, then basically you are working with a Poisson distribution. So that's the similarity that we have. The number of trials is unlimited, and the lambda, that is the expected value of the number of successors from the trials, is going to be constant. So having set down a little bit the different differences between these two distributions, now we can have a look at what are the conditions behind the Poisson distribution. To be able to apply the Poisson distribution, how shall we know that? In what are the conditions that needs to be satisfied to apply the Poisson distribution? Obviously, there's going to be some similarity between the binomial and the Poisson, though there's going to be differences, but there is going to be some similarities that you will see. So let's discuss that now. The first thing that we will need to note is that the Poisson distribution is usually used or usually applied in the context where you are dealing with the counts of rare events. That's the first thing. Now, there is something important here. Is that, as I said to you, the binomial and the Poisson are relatively similar in some way, because the Poisson is just a special case of the binomial distribution. And how is it a special case? Because we just saw that n is large, is very large. And also, the other thing that you need to note in the Poisson distribution is that we are going to take the probability of success to be as small as possible. That is, the probability of success in any given trial is extremely small, very, very, very small. That is the other thing, is that this is kind of tending to zero. The probability of a the probability of success is very, very, very tiny. That is the other thing that you need to note in the Poisson distribution. In the binomial distribution, this is not necessarily the case, but in a Poisson distribution, the probability of a success can be very, very tiny. This is why we say that we are dealing with a count of rare events, because the probability of success is very, very small. All right. So this is why I took the example of a number of car accidents. The number of accidents is supposed to be a rare event. Okay. So this is why we consider I use this example to illustrate the Poisson distribution earlier. That's already one thing, is that we are dealing with the count of rare events. Now, what are the other conditions that you should consider to apply the Poisson distribution? It's like in the binomial. We say that the trials are independent from the trials are independent. In the Poisson distribution, again, we are going to say that the events that we are referring to are independent. It's a little bit similarity as you see here. So the events are meant to be independent. But not only are they supposed to be independent, they are supposed to also occur randomly over that time interval or space. One of the things that they are independent, the other thing is that the case that they are independent is that because we said earlier NP is fixed from trial to trial, all right? So uh, that's one reason why we say that they are supposed to be independent. The other thing is that the event should occur randomly over a time interval or space. If we are referring to a certain time interval, let's suppose during a day from the start to the end of the day, we assume that these events, if they were to occur, let's suppose an accident was to occur, it would occur at any point in time here with the same probability. In other words, it means that you cannot have a higher probability, for example, you cannot have a higher probability of having accidents in the beginning of the day and a lower probability of having accident at the end of the day. If this is the case, then you cannot apply the Poisson distribution because it is not abiding to the principle that these events should occur randomly over that time interval. So I repeat, for you to be able to apply the Poisson distribution, you need to ensure that these events that you are referring to occur randomly over that time interval, which means that any point in time, they have the same probability of occurring. For example, not at the beginning, they cannot have a higher probability, or they cannot have a high probability of occurring at the end of a day, things like that. And then the other thing is that we have already mentioned it earlier, is that we say that NP is assumed to be fixed. You remember for the case of a binomial, we said that when we compared the binomial and the Poisson, we said in the case of a Poisson, we say that NP should be fixed, which means, in other words, for us, we're not going to write it NP, we are going to write it as lambda. Lambda is assumed to be fixed. Lambda is assumed. Lambda, it means what? Lambda means the average rate of occurrence of the event. Average rate of occurrence of the event. Now listen to me as you note here. Where if we are evaluating the probability of, let's suppose, having 2 accidents within a certain day, then we need to know what is the average number of accidents per day. What is the average number of accidents per day? Is the average number of accidents per day 1? Is it 1.2? Is it 1.5? It can be any value, by the way. Do not think that when we are talking about the average number of accidents, it should automatically be discrete. It can take a continuous value. It can be 1.5. It can be anything. But x cannot be anything. X should be discrete, obviously. But the lambda can take any value. It can be 1.5, it can be whatever. So if I say, for example, 0.5, it is equal to 0.5 per day. 0.5 per day. What does it mean? It means that we have one accident over 2 days. Over 2 days, we have one accident. So that's what the 0.5 means. So just to sum up, we said that to be able to apply the Poisson distribution, we are dealing with the count of rare events. That's the first thing. The second thing that we also said is that these events are meant to be independent, just like in the case of a binomial where the trials are independent. Then we also said that apart from being independent, these events should occur randomly over the time interval or space. Occur randomly means the same probability of occurrence at any point in time here. And then the last thing we said is that the average rate of occurrence, which is lambda, should be fixed, should not change. It should be the same over the period of interest. Now, it's important to note that, as I said to you, that these events should occur randomly over the time interval or space. You should not think that the Poisson distribution is always about time. There is also a case of space if you are talking about the number of misprints in the page of a book. So here the page represents the space, in other words. It's not a time factor, but it's going to be considered as space. When we refer to space, we are not referring to time here. We are referring, for example, number of misprints in the page of a book. So it all depends on the question what you have. So that's a little bit how you will know the conditions where to apply the Poisson distribution. Now, more concretely, if you have a question in exam, for example, how would you know whether you need to apply the binomial and how would you know whether you need to apply the Poisson distribution? It's very simple. In the binomial, you have two parameters, n and p. That is, you have a certain probability of success that is given and a certain number of trials. But in the Poisson distribution, you will see that there is no two parameters, but there is only one parameter, which is the average rate of occurrence. That is, how many accidents do we have per day before we start evaluating the probability of x equal to 1 or x equal to 2 or whatever. How many accidents do you have? The average number of accidents. So you see clearly that here, for Poisson distribution, you are going to be generally given a certain rate of occurrence or an average that is going to be given to you. But in the context of a binomial, you will be generally given a probability to work with. All right, you'll be generally given a probability to work with, the probability of success. So that's a little bit how you know how to apply, when to apply the binomial and when to apply the Poisson distribution. Now, when we have been referring to the Poisson distribution, what is this Poisson distribution normally? This Poisson distribution takes this formula here. Now, normally, just for your information, this e power negative lambda, lambda power x is, as we said, based on the fact that n tends to infinity and our lambda is assumed to be fixed as well. And we also consider the fact that p should be tending towards 0. All these information will make that from the binomial we can derive the Poisson distribution. From the binomial we can derive the Poisson distribution. And the Poisson distribution is given by this formula, where you will see the average rate of occurrence appearing in the formula here. The average rate of occurrence is appearing. So if I am interested in, let's suppose there is 0.5 accidents per day, and I'm interested in what is the probability of having one accident in a certain day, all right, in a particular day at the roundabout of, let's suppose, réduit. This is going to be just equal to e power negative lambda, because we are referring to one day, e power negative lambda, lambda power x, which is 1 in our example, over 1 factorial. That is as simple as that. Now, the other thing that you need to bear in mind is, let's suppose I say, what is the probability now of having one accident in 2 days? Here it's 1 day, but here I say 2 days. The first thing that you need to know is that if you are defining your random variable x, you would define your random variable x as the number of accidents per day. That's what you did here. But in the context of if you are dealing with 2 days, then you have to be careful. You cannot use x again because x was defined for 1 day. So you will have to use another random variable, whatever you could call it, x1, or you could call it y, whatever you will call it. Suppose I call it x1. x1 is the number of accidents in 2 days, over 2 days. Over 2 days. So if I've called x1 as a number of accidents over 2 days, then I can say x1 equal to, let's suppose, 1. I want one accident over 2 days. Then what I need to do is e power negative lambda. Now, what is x1? x1 follows what distribution? It's still a Poisson distribution, but with what lambda now? The previous one, for x, we said that the lambda is 0.5. That is the mean occurrence per day is 0.5. But if you're dealing with 2 days, and if you recall what I just said earlier, is that the NP should be fixed, that is, lambda should be fixed over the period of interest. What does this mean? It means that if one day we are dealing with 0.5 accident, then in the second day we assume that it is still 0.5. So in other words, over 2 days we are dealing with one accident per day. So in other words, it becomes the x1 follows now a Poisson with with the average rate of occurrence to be 1 instead of 0.5 as it was before. So it becomes e power negative lambda, lambda is 1 now, and lambda is still 1 power 1 over 1 factorial, if this was to be found. Now, if we were to look for 3 days, then it would be 1.5 automatically because you will still be adding 0.5 again. So it would be 3 times 0.5 if you were to deal with 3 days. So that's how you can basically apply the Poisson distribution. Now we can have a look at the conditions again. As I said, the count of rare events is one thing. Events are independent. Average rate does not change over the period of interest or space. An event should occur randomly over time interval or space. Now, the properties of a Poisson random variable, if you know that x follows a Poisson with a certain parameter lambda, whatever lambda could be, if you know that x is a Poisson random variable, then what you need to note is that if you want to find the expected value of x, this is going to be equal to lambda itself. So one other thing that you will note is that the parameter of a Poisson is the mean itself. The other thing that you will note is that the variance of the Poisson distribution is the mean as well. So it is the mean itself. This is one particular characteristic of that distribution. So the Poisson distribution is the only distribution where the mean and the variance are equal. You won't see that in the binomial case. You won't see that in other situations generally, except if you're dealing with a specific case of a binomial, which is a Poisson. But overall, you won't see that in any other distribution except the Poisson distribution, where the mean and the variance are the same. Now, we can have a look at some examples of where the Poisson distribution can be applied. Here we go. You have different examples, for example, modeling of number of claims in a certain insurance company. You will see that all these different examples are referring to counts of rare event. You are basically referring to counts. You are evaluating the probability of a certain count. Okay. Uh, that's how also you can differentiate a Poisson between a binomial. Because in the binomial, you evaluate the number of successors out of fixed number of trials, but in the Poisson, you just evaluate a certain number of events occurring, that is a certain count of events. And then the number of deaths in a specific time interval, count of bacteria in blood. All these are different examples of where the Poisson distribution can be applied among so many other examples that exist. You have this activity that I would ask you to do, obviously, and then we will get to discuss that later on in the class, of course. That was what we had for the binomial, for the Poisson distribution.